So the combined gas law, again, this is the one that is in your reference packet. It takes all of the three basics, Boyle's, Charles, and Gay-Lussac's, and it puts it together in one complex formula. Now, you will have, there will be problems where you will have to use all 6 variables. There will be some problems, guys, like on your test and quiz, where it'll just be Boyle's or Charles or, Gay-Lussac's, but you do not have those individually in your reference packet. So the way that I teach my kids to do this is that, okay, let's say you have just pressure and volume, you would cover up the temperature ones so you only have pressure and volume. Cover those up. I guess I can do it like this. Those would be gone. There's your Boyle's law right there. Okay? If you had just volume and temperature, you'd cover up the P's. There's Charles' law right there. If you had just pressure and temperature, you'd cover up the V's. There's Gay-Lussac's. So within the combined gas law, you have the 3 other basic ones depending upon what pieces are given to you. All right, so you will have to see, by writing down your variables, what pieces you have. Because again, by test day, you're going to have 8 or 9 formulas to choose from in a problem that you could use. Writing down those variables is so important that will guide you to what formula you need. So let's take a look here. This example It says, if 282 milliliters of a gas at 25 degrees Celsius and 1.3 atm is cooled at 20 degrees Celsius and 780 millimeters mercury, what is the new volume? So, lots going on. Start by pulling out the information that is important to us. 282.4 milliliters, what is that? Volume, we'll call it V1. 282.4 milliliters of a gas at 25 degrees Celsius. What's that? Temperature. What do we need to do that right away?
298 Kelvin.
Right. That's one that you may end up memorizing because 25 degrees is kind of room temperature, so a lot of examples use that. So it's 298 Kelvin. And then ATM is pressure. All right, so there's kind of my first conditions here. All right, then it says, what is the new volume? So I'm looking for V2. Now, typically when I write a problem, I like to have my volumes next to each other, my temperatures next to each other, and my pressures. All right, it's up to you how you write your variables in there, as long as I can see them, and the more you show me, the more credit I can give you. All right, so T2 and P2. So T2, they gave us 20 degrees Celsius. Convert that to Kelvin right away is going to be 293 Kelvin. Now, what do you notice about the pressure, folks? Yeah, they changed the unit. What do we have to do?
Convert it.
Convert it. Does it matter which one we go to? No, as long as they're both the same. Now, typically, guys, if I have the choice, I like to go to atmospheres because it's less numbers. It's going to be the smallest number to work with. How do I go from millimeters mercury to atmospheres? Divide by 760. So my P2 is going to be what when I do that? 1.02 atmospheres. So all I've done, guys, is write down my variables. Now I'll start worrying about my formula. I've got P1 V1 over T1 equals P2 V2 over T2. How do I clear the fractions? Same mathematical process as Gay-Lussac's and Charles. I'm going to cross multiply. So, just like this. But now I've got 6 variables instead of 4. So I have P1 V1 T2 equals T1 P2 V2. Bless you. Does it matter what order the left side variables are in? Or the right side variables? No, you could put V1, T2, P1 if you want to, and then V2, P2, T1. As long as these ones on the left are all together and the ones on the right are all together, that's what matters the most. How do I get volume 2 by itself? Divide by the other pieces there, just like we did yesterday. They will cancel out, be on both sides. So V2 equals P1 V1 T2 all over T1 P2. Now I can plug and chug. Folks, at this point, as long as you've written your units down in your variables, I don't mind if you drop your units in the formula itself. I'm going to do that right now because of the sake of space. But just make sure you keep track of them over there with your variables, and your final answer has to have a unit. Otherwise, you're going to lose a point. So P1 is 1.3 atmospheres times my first volume of 282.4 times my second temperature of 293 all over my first temperature of 298 times my second pressure of 1.02. Now, when you do the math, guys, I encourage you top times top times top. Then in the calculator, divide by bottom, divide by bottom. There's multiple ways you can do the math. As long as you get the right answer, it doesn't bother me. That's the simplest, most effective way. If you get in that habit every time, you're going to get the right answer every time. Who can tell me what you get for a final answer? So we'll call it, you said 373.7. We'll call it 374 milliliters. What did you put for your second pressure, though? Did you put 1.02? You didn't put the 3 like you said? Double check your math. It's really close, so it'd probably be okay. But maybe round it or something a little bit differently. Questions on this, folks? Need to amend this. Joe Milby was the one who got it wrong, not me. Of course I had to put it on the video. 354 milliliters is what you should have. Well, what was it? What did I just say? 374? Nope. I did. It was 354 when you round it to 3 sig figs. There it is. Man, that's what I get for listening to students. That's my fault. You try problem says a 700 milliliter gas. That's a what? Volume 700 milliliters of a gas at STP is compressed to a volume. So there's a new volume V2, 200 milliliters. Why is the decimal important there? Sig figs. And the temperature is increased. So this is going to be T2. It's 30.0 degrees Celsius. When you add 273 to that, you get 303 Kelvin. What is the new pressure? So you're looking for pressure 2. Well, where's temperature 1 and pressure 1? Right, folks, that's the key to this whole problem. STP, they will throw that into problems a lot, or I will. You've got to know STP, but do you have to memorize those conditions? Do you have to memorize them? No, because where are they? In your reference packet. Don't be too lazy to go there and look at those. Standard temperature, we need it in Kelvin, so we may as well use that one. Now, what pressure? Does it matter which pressure we choose? We could choose any one of them, but there's one that's a better answer choice for this problem, which would be what? KPA, because it says, what is the new pressure of the gas in KPA? Folks, when you're asked for standard pressure or using a pressure, you can use whatever one you want unless the problem asks you for a specific one in your final answer. Use that one then that they ask for. So this one is KPA, so my pressure 1 is 101.3 KPA. So now again, P1V1 over T1 equals P2V2 over T2. Cross multiply, we get P1V1 T2 equals P2V2 T1. I'm looking for my second pressure, so I'm going to divide by V2 T1. Those are gone there. V2 T1. So pressure 2 equals my first pressure, which is 101.3 kPa, times my first volume of 700 with a decimal point. Remember, sig figs, they do matter. My second temperature is 303 Kelvin, all over my second volume of 200 point, and temperature 1, 273. When I do the answer, when I do the math, my final answer is 394 kPa. How do we do? Got it? Is the math, guys, really anything different than Guy-Lussac's or Charles' Law? No, it's just there's that extra pressure variable. Now you have all of them. That video that I showed you yesterday of the railroad car, right? Which again, you can go back. It's on my YouTube channel. It's in that playlist. Folks, it's really the combined gas law that it's showing, because pressure does play an impact in that. It's not just volume and temperature, all right? Because what was happening inside the rail car, the temperature was decreasing, which decreased the pressure as well. So that the pressure on the outside, the atmosphere pressure, forced it to implode on itself and the volume. So there's a lot of going on within that crushing of a can or crushing of the railroad car. Questions with the combined gas law? If not, we're moving on, guys. We're going to talk about the next couple pieces here today as well. Dalton's Law of partial pressure. Basically, what you're doing here is you're taking the pressure of each gas in a mixture, guys, and that gives you the total. So your total pressure equals the sum of all the pressures. So right here, we have our total pressure, which sometimes it's referred to as atmospheric pressure. Make a note of that. Atmospheric pressure means total pressure as well. You just take the pressure from gas 1 plus the pressure from gas 2 plus the pressure from gas 3 and so on. If you have 15 gases, you add them all up, there's your total pressure. All right, it is that simple. Look in your reference packet. It is the fourth formula that is listed there in your reference packet, folks. Dalton's Law of partial pressure. All right? All you're doing is adding them up. So I could either give you all the separate gases and ask you to give me what the total pressure is, or I could give you the total pressure and then give you 2 of the 3 gases and you have to tell me what the third one is. How would you do that? You subtract them out. If I'm looking for the pressure of gas 3, I'm going to subtract out P1 and P2. And that's how I would get it. So here we go. Let's take a look at it. That's basically what you're doing there, guys, with the simple Dalton's Law of partial pressure. Now, there is a special case with Dalton's Law of partial pressure. It's where you're collecting gas by water displacement. What is water displacement again? We've done it before. Okay, you can't say displacing water. What are you doing, though? You're moving the water, you're pushing it out of the way by adding an object to the water, and then you can test and see what the volume is. Same thing with gases. You guys will be doing a lab later on in this unit where you're going to be doing that. So, what you're doing here with this formula, guys, you have your pressure of your atmosphere, and that's going to equal the partial pressure of the water vapor plus the partial pressure of your gas that you're collecting over water. So you have to include the partial pressure of the water. Flip to page 899 in your textbook. The blue textbook at the very back. So to solve a partial pressure problem, guys, where you're collecting the water over displacement, you need to go to this table. Start memorizing it. You've got 2 weeks to memorize that table. Just kidding. I'm just kidding. Guys, that table will be given to you on your test, all right? It'll be a separate page of that. You really thought I was going to make you memorize the table?
Yeah.
Are you? I'm not insane, folks. All right? I'm not insane. All right? Oh, my goodness. The homework took a half an hour? My goodness. That's just too long. All right.
Half an hour for every statement class, an hour for each honors class.
Exactly. So here we go. Here's an example, guys. Listen. Shh. I'm not going to do a class example with the basic one where you just add up all the individual gases and there's your total. We're going to do one with the water displacement method, though. That's what we're going to get into now. It says oxygen is collected by water displacement. The barometric pressure and temperature are as follows. What is the partial pressure of oxygen? So, what do you think barometric pressure means? The what? Pressure of what?
Barometer.
No, folks.
ATM.
That's your atmospheric pressure. Let's focus. All right, a lot of times problems will say barometric pressure. That's just your atmospheric pressure. And that is 84.5 kPa. So we can jot that down. All right, pressure of our atmosphere is 84.5 kPa. Are we at sea level? No, why not? Where are we? We're somewhere in the, probably somewhere in the mountains, right? Because it's lower pressure than sea level. Now, it also gives us a temperature, 20 degrees Celsius. We're looking for the partial pressure of oxygen. In that formula that I just wrote out, was temperature involved here at all? No, it was not. What do you think the temperature is going to play a factor for? What's it going to help us find? Because what are we missing from this formula that we weren't given? What gas? We're looking for the pressure of our gas. That's oxygen. Oxygen is the gas we're looking for. What else are we missing? The pressure of the water, folks. So we were not given the pressure of the water. We've got to find that. The temperature is going to help us find that pressure. So what you're going to do is you're going to go to that table. And remember, on your test or quiz, that will be given to you. You're going to look for 20 degrees Celsius. Notice there are multiple pressures that are on that chart. Which one do we want to use for this problem? kPa, right? Because we're given our pressure for the atmospheres in kPa. So when you go to your table and you see 20 degrees Celsius, what is the pressure of the water vapor at 20 degrees Celsius? 2.34 kPa. Now, all we got to do, folks, is find our formula and plug it in. So the pressure of our atmosphere equals the partial pressure of the water vapor plus the partial pressure of our gas, which in this case is oxygen. What piece am I looking for here? Pressure of the oxygen. So when you get that by itself, I'm going to subtract my partial pressure of the water vapor out. Those are gone there. So my pressure for my oxygen is just going to be the atmospheric pressure minus the pressure of the water vapor. So I had 84.5 kPa minus 2.34 kPa. So my pressure for oxygen is going to equal what? Do the math. 82.16. Let's round that to the nearest one, which should be 82.2 kPa. Easy? Guys, Dalton's Law of partial pressure, all you're doing is adding or subtracting, depending on what it's asking you for. That's it. Sometimes they may give you the partial pressure of the gas, and then say it's collected over water vapor. What's the total pressure for that day? You just add them up. Okay? That's all we're doing is adding and subtracting here. All right. Moving on. Here you guys try this problem on your own. All right, so this is what you're given in this problem. Temperature, pressure of the atmosphere. We've got to use the temperature to figure out the partial pressure of the water vapor. 50 degrees Celsius, what's our partial pressure? 12.34 kPa. Again, since we're given kPa for our total atmospheric pressure, we may as well use that one. All right, so now partial pressure of the atmosphere, or the pressure of the atmosphere equals the partial pressure of the water vapor plus the pressure of the gas. All right, pressure of our gas is going to equal the total, which is 101.1 kPa, minus our water vapor of 12.34. Pressure of our gas, then, is going to equal what? 88.76, so we'll round it to 88.8 kPa. Josh. Sig figs, it would be actually 4 sig figs there, so it would be the 88.76. It would be. Because you wouldn't look at your temperature value there for sig figs, you would look at your pressure values, since they're the only ones that are actually in the equation. Actually, no, I'm sorry. It would be exactly what we have up there. It would be this because we're subtracting, we're not looking at total number of sig figs. All right, so when we subtract or add, we look at the least number of decimal places. This one has 1 right here, this one has 2. So this is correct sig figs right there. Because we're going to the least number of decimal places when we add or subtract. My apologies there. All right, last thing we're talking about today, guys, is Graham's Law. What is diffusion? Mixing of 2 or more gases. Is it just gases? No, it could be liquids as well. Do solids diffuse? No. Yes, they do. Very, 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 very slowly and only at the surface. Effusion. What is effusion? Passing through a small opening. Folks, here's what it is. The rate of effusion or diffusion, whichever one you're asked, all right, varies inversely. What does inversely mean? Opposite. With the mass of the gas. So, we've already talked about that. The higher the mass, the rate is slower. The lower the mass, the higher, the faster it's going to move. Okay? So here's what it looks like, guys. This formula is not given to you. All you got to remember, guys, is gas A over gas B is the square root of the mass of gas B over the mass of gas A. So you flip them. That's how you get that inverse piece there. It is a square root. Let's take a look here. We're going to compare the rates of effusion of hydrogen and oxygen at STP. How do we write hydrogen? H2. So we need to know the mass of hydrogen. That's going to be what? Nope. 2.016, right? Because it's a diatomic. It's part of Brinkelhoff. Is oxygen part of that as well? Absolutely, O2. Now, folks, if you forgot to multiply these ones by 2, it wouldn't matter in this problem because they're both diatomics. You'd still get the same ratio. But when you get to an example where you have one gas that's not diatomic and one that is, that's where you will fall into that trap. This is going to be 32.00. So, it doesn't matter which one you call gas A and gas B. I typically will go left to right. So hydrogen we'll call A. This one we'll call B. So it's going to be the rate of H2 over the rate of O2 equals the square root of which one over which one? I'm just going to rewrite my formula up here. So it's the mass of B over the mass of A. So in this case, it's going to be oxygen, 32.00, over hydrogen, which is 2.016. So our rate, I'm running out of space here. Our rate of hydrogen gas to oxygen gas equals the square root of, basically it's what? It's basically 16, but do the math, guys. 32 divided by 2.016 equals, you guys have calculators, start punching it in. What's that? 15.87. Take the square root. Equals what? 3.98. So, how you answer the question, guys, for this? You would write something out like the rate of hydrogen to oxygen, the rate of, really it's effusion, the rate of effusion of hydrogen gas to oxygen gas is 3.98 times faster. All right, 3.98 times faster. That's how you answer the problem. You have to say how many times faster is the one gas to the other. All right, whichever one you call A to B. You guys try comparing the rates of effusion of fluorine and chlorine. So fluorine, again, diatomic, it's 38 is the mass. Chlorine, diatomic as well, 70.9. So I'm going to go fluorine is gas A, chlorine is gas B. So my rate is going to equal the square root of the mass of B, which is, in this case, 70.9 grams, divided by 38.00 grams. Grams will cancel out. So the rate here is going to be, when you do 70.9 divided by 38, what do you get? 1.87. You take the square root. Your final rate is 1.37. All right. Now again, you got to write a final sentence saying that fluorine effuses 1.4 times faster than chlorine. Something like that is how you would answer the problem. Got it? Questions? Is it easy? Is it hard? All right, it's pretty easy. Folks, the one thing though, Graham's Law, that formula is not given to you in your reference packet. You've got to remember that rate varies inversely with mass. So really the higher the mass, the slower it's going to be. All right? All right, homework time.